Alright, in this video, we're going to be talking about direct and inverse variation. Right, that's what the paper says, yes. Okay, so direct variation is essentially when things relate to each other. So it's like the more you study, the higher your grade. Usually, I mean, some people don't have to study, whatever, but you would think, like, the more you review the content, the better your grade will be. Most of the time it's true. With inverse variation, it's like when one thing goes up, another thing goes down. So it's like, maybe the more time you spend, I hate using this one because it's always used. The more time you spend watching TV, the less likely your grade will be high. So like usually the more time you spend watching TV, the lower your grade will be. Something else. The more you spend on so if like you're selling something, the more you spend on material cost is usually the less profit. No, that's not true either. But as something goes up, another thing goes down. So biggest thing here, notice both of these equations have a k. The k is called our constant of variation. So I'll write that out for you real quick. Constant of variation. Yeah, that's spelled right. Well, let's knock that off. The constant of variation is just like a number that it is changing by each time. So like, say you make $8 an hour or something like that. If we make $8 an hour, our constant of variation would be 8, and it would be direct variation because the more hours that you work, if that was time, the more money you would make. Dollar bills, yo. So that would be direct variation. As you spend more time at work, you'll make more money, right? Constant of variation is just a number, what it's changing by each time. All right, so looking at this first one here, determine the type of variation, one of those two, and the equation for each graph. So let's take a look. X is 500, X is 1,000, X is 2,000. We're talking about the depth and the temperature. So this is probably the depth in the water and the temperature that it is in Fahrenheit. So say I'm 500 feet down, it's about 28 degrees. 1,000 feet, 14 degrees. 2,000 feet, 7 degrees. So it looks like as I go further down, or more depth, a greater depth into the sea, or the floor, or not the floor, the soil, the earth, that's what I'm looking for, the lower the temperature. So the deeper I go, the lower the temperature. So my guess is since I'm going a greater depth and a smaller temperature, then this is going to be inverse variation. So if it's inverse variation, remember our equation was y equals k over x for inverse variation. So if that's true, if y equals k over x, then k would equal xy, right? If I just multiply the x to the other side. So what that means for us is that the k has to be the same for every x and y value we have. And if we multiply them together, that will give us our constant of variation. So here, if I do 1,000 times 14, k would be 14,000. If I do 2,000 times 7, k would be 14,000. If I do 500 times 28, k is 14,000. So moral of the story, all of our k values are the same, so we know we have a constant number that our values are changing by. That's our constant of variation. So what that tells us, since we checked inverse variation, right, when we did k equals x times y, all of the k values were the same. So what that tells us is this is definitely inverse variation. Now to give the equation, because it says in the equation, I'm just going to use that k value in my constant of variation, or as my constant of variation. So my equation would be 14,000, because that's what k is, over x. I'm going to leave y and x in the equation and put in my constant of variation. That's it. Magic. Yes! All right, moving on. Get back, computer. You're way too close to me. Get back! All right, moving on. All right, so this one looks different. So since this one looks different, let's take a look at the numbers. 1, 2.5. So my x is 1 and 2.5. And then the y was 2.5. And then I have 2, 5, 3, 7.5, 4, 10, 5, 1, 12.5, 6, 15. So it looks like as the x values go up, the y values also go up. So my guess is this is direct variation. So since this is direct variation, y equals kx would be kind of the formula that we want to check. And notice, if I solve for k in this one, I have to divide by x. So y over x should be my k value. So let's go through and check that real quick. So if I do y divided by x, k is 2.5 in this case. 5 divided by 2 is 2.5. 7.5 divided by 3 is 2.5. 10 divided by 4 is, you guessed it, 2.5. Hey, I bet 12.5 divided by 5 is 2.5, and it is. I don't know what I said. I think I said 2.5, right? And 15 over 6 is also 2.5. So the k value throughout all of this is 2.5. You could also write this as 5 over 2 if you want. Makes no difference to me. But that tells us, since all the k values are the same, this is indeed direct variation. And to write the equation for it, I would just write y equals 2.5x, or y equals 5 over 2x, either way. So now I know you see a fraction and you think inverse variation, but this is 5 over 2 times x, not 5 over 2x. So notice inverse is our, what do we even call them? Rational functions, that's right. And our direct is like a linear function. All right, so some examples of each type of variation. Direct has to be some number times x. So any number times x can be a negative number. Makes no difference. What it cannot be, no, is anything plus a number. My fries are ready. I'm going to finish this real fast though. Cannot be anything minus a number. Cannot be anything other than that we see right there. All right, that's annoying. So I'm going to go get them real quick. They're not ready yet, so I have 4 minutes before my fries are done. I'm going to eat them. I'm sorry. I just mowed the yard and it's really hot outside. I don't know why I have more energy now though. All right, anyways, inverse variation. So some examples of this is some number over x. I have to have an x in the denominator, and it doesn't matter what number is on top. What it is not though, no, is anything else. So 3 over x plus 1, or, and it could be like 3 over 2x, that's fine too. You could see that, that's fine. That's still inverse variation. Cannot be 2 over x plus on the outside. How about plus a monkey? Yeah, that makes sense. That's a real equation, don't question it. It has to be of this form, where we have a k divided by an x or some other variable. But it's two variables, constant variations on the top. All right, so now let's see how we actually use these things. So we have the amount of time in hours it takes to fill a swimming pool varies inversely with the rate at which the water is pumped. So that's telling us our equation right there. So it says the amount of time varies inversely at the rate at which it's pumped. So notice it gives us time t varies inversely with r. So the equation here that we're going to use is t equals k over r. Time varies inversely with the rate at which it's pumped. So now it goes on. It says the constant of variation is 6. Well, that's nice. So we know our equation then is 6 over r. That's kind of the equation that we're going to use. Find how long it will take to fill the pool when the rate is this much. So it's telling me rate, and I want to know how long it will take. So I'm looking for the time. So I can use t equals 6 divided by the rate it gives me. Type it in our calculator, if I had one. I don't even need one because I got the answer anyways. So we'd have 1.82 hours. That was the time that would be at that rate. Alrighty, moving on. This is the best example. I think there's another good one. A monkey is taking a 5-mile journey through the jungle. The monkey wants to reach his destination in 40 minutes. How fast should the monkey walk in order to get there on time? So here we kind of have to think about this one, because in order to go somewhere, the amount of distance that we travel is equal to how fast we are traveling for how long. So we're going to use this equation, distance equals rate times time. Right? So think about it, if you're going 30 miles an hour for 1 hour, you've traveled 30 minutes. But if we're going 30 miles an hour for 2 hours, then we will have gone 60 miles, right? We have to do 2 times 30. So this equation is used. Apex isn't going to give you this equation, so make sure you guys write it down, get it down. It will be using this. So remember, distance is the rate times the time. My fries are ready again. All right, so now that we know that, if he's going 5 miles, that's our distance. I don't know the rate, right? Because it's saying how fast should the monkey walk. That's our rate times the time, 40 minutes. So now what they're going to do, we're not going to use minutes. Time is always measured in hours. So 40 out of the 60 minutes in an hour. So now we can solve that. So I would multiply by 60, divide by 40, or just do times 3 divided by 2. So 5 times 3 divided by 2 gives us 7.5. So that means we have 7.5 miles per hour is how fast that monkey needs to walk, which is manageable. He can do it, I believe. He's going to get to that banana. The banana in the sky. All right. Volume of a gas in cubic centimeters, V, varies inversely with the pressure of the gas, P. So we have volume V varies inversely with the pressure P. So I know I have V equals K over P. When the volume of the gas is 18, the pressure is 22. Find the volume of the gas when the pressure is 2.1. So this one is not giving me the constant of variation, but it did give me enough information to figure it out. So they gave me when the volume is 18, so I know the volume is 18, the pressure is 22. So I have K over 22. This will allow me to solve for that K. So what I can do now is just multiply that 22 times 18, and K is 400 minus 4, so it should be 396, but I want to make sure. Look at that, 396. All right, so 396 is K, so that means my equation then is 396 over P. That's our real equation that we're going to use. So now, it says find the volume when the pressure is 2.1. So I will have the volume. I have that 396 divided by 2.1. So I'm going to divide that. And I get the volume should be 188.57. Let's see how our volume was being measured. Centimeters cubed. So centimeters cubed. There we go. All right. Got one more down here. The rare giant banana of Madagascar. I'm sorry. I was tired when I was typing these. So the height varies directly with the length of its shadow. So the height varies directly with the length. So I'm going to say H equals K times L. A banana that is 4 feet tall casts a shadow that is 9 feet. How tall is a banana that casts a shadow that is 13 feet? So again, let's figure out what our constant of variation is. So I know the banana that's 4 feet tall, so 4 foot, equals K times the length of the shadow was 9 foot. So if I divide by the 9, that means K is 4 over 9, or 0.4 repeating. So now, I have my equation, height equals 4 over 9 times the length. So to figure out how tall a banana is that casts a shadow that's 13 feet long, I can just put in 13. So height equals 4 over 9 times 13. So 4 times 13 divided by 9 gives me 5.78 feet. Alrighty. Hopefully this video was helpful for you guys. As always, please let me know what questions I can answer for you guys. I'm always here for you. Just email me, reach out, and I will get to you back to, I'll get back to you as soon as possible. All right, I'll see y'all soon. Bye.